Hi everybody, welcome to our new online classroom. Thank you again for being flexible in all of this. I know this is not the class you signed up for in the beginning. It's not really the one I signed up for either, but we're gonna make it through this the best we can. So the videos that I wanna post, I don't wanna post 2-hour-long lectures or hour-long lectures because one, I don't think it would be that much fun to watch. I don't think I'd sit there and watch a math video for an hour. And two, I just want to be more flexible in your time management. So I want to do these videos that are like 10, 15 minutes so that they're easier to kind of work your way through and so on and so forth. So that means I'm not going to do every single example in the notes. I want to just kind of highlight the ones that I think are a little bit trickier or the ones that are a little bit more in depth. And then the rest of them, you guys can look at the stuff that I've posted online. So the note packets are going to come in two formats. One of them is going to be blank, and then the other one is going to be completed. So you can look at those and compare them. And if you have any questions on anything, just email me, contact me during office hours so you can Zoom, and I'll answer whatever questions you have. So we're going to pick up right where we left off. So that was 7.3. We did 7.1 and 2 in class. So we're going to start by solving trig equations. So let's get into it. So we're going to solve the equations over the interval from 0 included all the way up to 2 pi. But we're not going to include the 2 pi. And this is going to be your like your default interval. I'm not going to ask you for every single solution, just the ones that are going to fall within this interval here. That's typically what you do in calculus, so we're just going to follow that system. So let's do the first example just to get us into it. So 2 sine of theta plus 3 is equal to 2. So your goal for these, there's just the one trig function in there, just get it by itself. So however you need to do that. So this one, we're going to subtract the 3. And then we're going to divide it both sides by 2. And now you're in a position to where you can solve for theta. The trig function is all by itself, so now you can get the angle. So you can use, the unit circle, you can use SOHCAHTOA, however you were taught or whatever method you like to use, keep using that. I'm not going to force you into one method over another. So for sine of theta is equal to a half, or negative 1/2. On the unit circle, or if you use SOHCAHTOA, that would put you in quadrants 3 and 4. 3 and 4. If you use SOHCAHTOA, just draw your triangle, label up your sides, and then if you use Pythagorean theorem or recognize the triangle that you have, these sides are root 3s. This one's got the negative because it's on the negative axis. So now just figure out the angle inside of there, which would be a 30. Because that's your 30, 60, 90 triangle. But you don't want the angle that's inside the triangle. That wouldn't make any sense. That wouldn't put you in those 2 quadrants. So you got to figure out what rotates all the way over there. Starting at 0, what rotates all the way to that angle? Well, that would have to be 210. Or 7 pi over 6. And then the same thing to rotate around to quadrant 4. So that would be 330 degrees, or 11 pi over 6. And now you're done. So typically you're going to get 2 solutions for the most part. unless there's other trig functions in there. Sometimes you only get one, like if you're landing on either the x-axis or the y-axis, there might only be one solution. But you're going to generate more than one solution most of the time. Okay, so let's move down to part C. So 4 cosine squared is equal to 1. So again, there's only the one trig function in there, so let's get it by itself. So divide both sides by 4. And it's really close to being by itself, but you've got this annoying little square in there. So to get rid of it, square root both sides. And if you introduce that square root on your own, like it wasn't there to begin with, you also want to put that plus or minus. So plus or minus 1/2. And now you're in a position to solve for theta. So when it's a plus or minus like this, I kind of like that because that tells me I'm in all 4 quadrants. So if I can figure out the angle in quadrant 1, then I can just sort of match the other ones up to the angle I found. So in quadrant 1, when cosine is 1/2, that is going to be pi over 3. So then the rest of the answers are the reference angles that match up to this. So when they match, that means your denominators are the same. So that's the one in quadrant 2, quadrant 3, and quadrant 4. So if you're really good with your unit circle, and you know the other angles that match up to that, just fill them in. So 2 pi over 3, 4 pi over 3, and 5 pi over 3. I'm really sorry, I can't ask for any questions on this like right now. That would be a little freaky. But if you have questions on this, please email me, contact me through Zoom during office hours if you're just totally lost. Hope you're not. Okay, so let's move on to example 2. So now we're going to make them a little bit trickier. So we're not just going to have just an exponent involved on a single trig function. Now you're going to have like multiple sines, multiple cosines, different trig functions together, different exponents in there. There's a lot of things that we can do to these. So we're still solving on that same interval from 0 to 2 pi. We're not going to change it. So let's start with 2 sine squared of theta minus sine of theta minus 1 is equal to 0. So everything, like your trig functions are all on the same side. So one thing to note about this is that it is a trig equation, but it's also another type. It's also quadratic. So you can have combinations of types of equations kind of mixed together. So quadratics and trig equations, natural logarithms and trig equations, natural logs and quadratics, quadratics and exponential. I mean, we can have multiple types of equations kind of all embedded into one. So if you have a quadratic equation mixed with another type, the quadratic equation is like the boss. He's the one that tells you like what you have to do. You have to start solving that type of equation, that quadratic, you have to start solving that thing first. So that means you have to factor it, you have to complete the square, or even use the quadratic formula. So this one in particular is going to factor. So 2 sine of theta plus 1, and then sine of theta minus 1. And then once it's factored, just solve for each factor to 0. So sine of theta would equal a -1/2. Hey, we've seen that before. Or sine of theta would equal a +1. So this one, we just solved it. That was the first example we did. So the answers are still 7π/6 and 11π/6. And then for this one, sine of theta equals 1. Well, sine equals 1 when it's right up at the top of that unit circle. So that means it's going to be 90 degrees, or pi/2. If you kind of notice a little bit, we're not giving our answers in degrees because our interval told us that we had to be in radians. And we're typically going to be in that mode because in calculus, that's predominantly the mode that you're in. So stick with the radians, unless it says otherwise, but it didn't. Okay, so moving on to example C. Sine squared minus cosine squared equals 1 plus cosine. So we've got a little problem with this. We have two different types of trig functions running around, and you've got like a single cosine on the other side. So if you can get all of the trig functions to match, so they're either all sines or they're all cosines or they're all tangents, that's your goal. Having one type of trig function in the equation is easier to deal with than having two or sometimes three. So we're going to change this, either the sines into cosines or change the cosines into sines. So which one do you think would be easier to do? Probably changing the sine into a cosine. So sine squared, we can use an identity with that, and that was from our previous section, that Pythagorean identity. Sine squared plus cosine squared equals 1. We're going to use it, because if you swing the cosine squared over, now you know what you can replace that sine squared with. So 1 minus cosine squared is going to go in for just this term. And we're going to leave the rest of it the way it is. And you don't need to surround it with parentheses. I just did it, so I don't know. Just I thought it helped distinguish it from the rest of it. But you can delete them out if you don't like them. All right, so let's go ahead and combine like terms. And hey, you've got another quadratic type of equation again. So just like here, we're going to try to use the quadratic method. But first, we got to set it equal to that 0. So your squared term is negative, so I'm going to move it over to the right just to make it a positive. So we're going to put 0 on the left. The 1s are going to cancel. And I can factor cosine of theta out. And then I can solve for each factor. So the first one, cosine, just want to know where does it equal 0. And then the second piece, the factor, I want to know where cosine is equal to a -1/2. So cosine equals 0 when theta is either just straight up or it's going straight down. So pi/2 and 3π/2. And then for this one over here, when it's a negative, you're in quadrants 2 and 3. 2 pi over 3. And 4 pi over 3. So I wanted to do one other problem from this set, and that was example E, just because it's a little bit different. So that's where cosine of theta is equal to secant of theta. So we're going to start by changing secant into cosine. So in order to do that, that's where you're using that reciprocal identity. Because remember, it's easier to solve a trig equation if there's only one type of function in there. So we're going to go for just all cosines. You could switch it to all secants if you wanted to. That would just mean you would change this thing out. You can go either way most of the time. This one, it would have been a little difficult to change that out. You need a square root, which, ugh. So anyway, so let's get rid of the fraction. Getting rid of fractions is always nice. So cross multiply. Square root it. And again, if you introduce that square root yourself, put that plus or minus in there. And then cosine is going to equal a 1 when theta is 0, and it's going to equal -1 when theta is pi. So let's move on to example 3. And these, there's only going to be the one trig function in there, but it's going to have something a little bit different than the others. So sine of 2x is equal to a half. The other two examples, example 1 and example 2 and all the parts in there, none of them had a number sitting in front of your variable. So when that occurs, you don't need to use an identity with it. All it does is it just tells you that you're going around the unit circle more than once. So you're going to have a lot of answers with these because you've got to make more than one trip around the circle. And if you're going, well, how do you know how many times? It's the number sitting in front of the variable. So that 2 tells you that you're going to go, or it tells you the number of times around the circle. So the 2 just says, hey, we're going to go around the circle twice. So when you go around the circle like more than once, that means you're going to have to add 2 pi to your answers until you've got all of them around, however many times you have to go around. All right, so let's see what I mean by that. I think that was a little cryptic. Okay, so with this, just figure out just pretend the 2 isn't in there, just cover it up. And go, okay, where does sine equal a half, a positive 1/2? So it would equal a positive 1/2 at pi over 6 and 5 pi over 6. So that's what the angle would have to equal in order for sine to be a half. Well, what's my angle? Well, the angle is 2x. So 2x would have to either equal 5 or pi over 6 or 5 pi over 6. So just get your answers around just the one time. Once you have them, then you can start to rotate around the circle as many times as you need to. So we just need to go around twice. So add 2 pi to each of these answers. So pi over 6 plus 2 pi, and if you got a common denominator, that would be 13 pi over 6. And then if you added it to 5 pi over 6, and again, found a common denominator, that would be 17 pi over 6. Now, some of you I know are going, wait a minute. Aren't we supposed to solve for the interval of 0 to 2 pi? Well, yes, you are. But you're not done yet. Like, these are not your answers. It really seems like they are, and a lot of people just circle them and stop and say, hey, we're done. But you haven't told me what x is. You've told me what 2x is equal to. So you gotta get this x by itself. So you're gonna create your list of answers. Once you're done creating the list, then you can solve for x. So to solve it, you have one of two options. You can either multiply by or divide by 2, which is fine. You're just going to divide your fractions by something. Or multiply everything in there by half. So the left side is just your x. Multiply the 1/2 in there. Reduce it if you need to. So pi over 12, 5 pi over 12, 13 pi over 12, and 17 pi over 12. So you now have all of your solutions, and now they all fit in that interval from 0 to 2 pi. So let's try another one. Let's try cosine of 3x is equal to negative root 2 over 2. The negative root 2 over 2, you can think of it in a different way. You can write it in a different way. That matches up to your unit circle. Because this isn't really a point on the unit circle, nor is it one of the sides for SOHCAHTOA. So you can unrationalize it and go with this if you need to. You don't have to, but it's there if you need it. So the 3, just like that 2, tells you, hey, I have to go around the circle 3 times. So get your answers for the circle once. So where does cosine equal a negative root 2 over 2 or a negative 1 over root 2? Well, that would have to be 3 pi over 4 and 5 pi over 4. So that's around once. So now keep adding to pi to give you a second time around the circle, and then again for a third time around the circle. So add 2 pi to each of these. So 11 pi over 4 and 13 pi over 4. And then we're going to add 2 pi again to give you the last time around the circle. So add 2 pi to each of these. So 19 pi over 4 and 21 pi over 4. And then take your angle, which is 3x. That's what 3x is going to equal, all of these, and now solve for x. So you can multiply everything by a third. And if it reduces, reduce them. So the third, if you multiply it to that first answer, 3's cancel. So pi over 4, 5 pi over 12, that's fine. 11 pi over 12, doesn't reduce. And then keep going. Keep going. You get to the last one, you got 21 pi over 12. Well, oh no, that one reduces. So don't panic, just reduce it. So 7 pi over 4. So you got all of those answers for x. Okay, So I think that'll pretty much do it for 7.3. You can find the rest of the notes filled in online under the modules tab. And again, if you have questions on this, please contact me. There are other videos you can look up on YouTube if you need to reference them. But contact me if you need anything. So yeah, okay. Thank you, and we'll start 7.4 in a moment.